I was like, that's why I like this. I can't do it.
I can't really either. It's kind of full, but.
Well, this is literally I haven't shaved for like 2 weeks.
Really?
Yeah.
Really?
Yeah. Chappie has a shave. Wait, do you shave?
I shave like almost every day.
Oh yeah. Yeah, this is I have like these 3 hair that I get, and that's it.
I got kind of lucky because my dad can't. He's like hard. I am too.
Hallelujah. Hallelujah to what you wrote on the board.
I don't know binary.
Tanner.
I do not know. I kind of not, but I don't see anymore.
I saw you. We're even in classes together. So
Except for in this class.
I mean,
I've never seen something more elitist in my life.
How is that elitist?
that is elitist. What is that? No, I'm in thermo. No, I'm not in dynamic. Because I don't have to.
No, it's because you do that.
You're going to be an engineer.
You really not know
Well,
binary?
okay.
I've had people explain it to me 5 times, just keep forgetting.
It's just base 2. Like we work in base 10.
It's just something that I haven't put effort into memorize.
It's just so that's just 2 in binary.
What happens if it's 0 and then 1?
Well then, in the same way in decimal, the 0 in front doesn't matter. Then it's just 1.
Yeah, it might.
Because it's like we work in base 10.
No, God, no.
Oh,
I'm holding a mark. Yeah, I'm holding a blue mark. So.
I mean, that one was green. Wait, that one looks green.
Wait.
That's not green, Chappie.
So I saw the green.
That's
So
not
there's
green, Chappie.
definitely green on the side, and that's what I saw.
What
I
is
did not
happening?
look at the black cap. I looked at the green writing on the side.
You didn't see either the black front or back.
No, you threw it on the ground.
I didn't throw it on the ground. It just didn't exist.
See, like this is
Oh,
111.
Jesus, the create matter.
10, 1, 10, 0. Like that's how we work. This is base 10. But in base 2, it's 2 squared, 2, 1, 2, 0. So it's 1 plus 2 plus 4. And so that's 7.
Very sad for them. Oh. See, that's why we go to college and do higher math.
So fairly simple. I've had to explain 3 different time systems.
Yeah, I just see. I know it now, and it's like, okay, I'll understand. It's fine. It's easy. I won't remember this in 2 months.
I mean, just remember it's base 2. It's just base 2. Welcome to maths.
Okay, it is 2:45. So, is it? Yes, it is. Welcome to maths. I hope you're prepared to do some math today. No.
Yes, sir.
Wrong class.
Because it's math class, and we're gonna do some maths in math class today. But before we do that, let's pray. I'm not sure. Actually, you know what? If I had to be completely honest, I have no idea whether Dr. Lang is sick, or if he was in contact with someone who was sick, or his family. I don't know what's going on. Anyway, let's discuss up his family first, because he's not here right now due to probably COVID reasons. So, Heavenly Father, thank you for this afternoon. Thank you for this really amazing class, students. I pray that you would bless our time together, that we would be able to move swiftly and efficiently and productively through the math that we're going to cover today. I also lift up Dr. Lang and pray for healing for his family, for himself, and that there will be no long-term negative side effects from the sickness coming forward. Just bring rapid restoration for his body and for anyone else who is sick. In Jesus' name, amen. So, yeah, I'm going to assume that you guys didn't start the homework after I extended it to Monday. Yep. So I'm gonna do you a favor and get your brain warmed up to what you're gonna have to be doing. So we're gonna do some exercises. So these are all gonna be solve the initial value problem.
Professor Salem.
Yes, sir.
Was Monday, what is it? Was Wednesday's lecture only 2.1? Or was it 2.1 and
It was,
2.2?
okay. So we're gonna cover a little bit of the 2.2 that we didn't get to on. Wait, today's Friday.
Yeah.
Oh my gosh. Okay, we got a lot to do then. So x, y prime.
I need extra.
It was at least 2.1.
Plus 1 plus or 1 plus x cotangent x times y equals 0, and then the initial condition is y at x equals pi halves is equal to 2. Okay. So this is an equation,
Homogeneous.
and would anybody like to throw out the pretentious vocabulary we have here?
Homogeneous first order linear.
The champion knows what's up.
What's up.
What we're gonna do is we're gonna now note that it's already homogeneous, so we don't need to take this, we don't need to worry about solving the complementary equation and getting a y1 and all that jazz. So we can just solve directly for y. And here, y'all engineers, you need procedure. So
We love procedure.
1, you want the coefficient of y prime to be 1. So coefficient of y prime to be 1. Wow. That'll just make your life infinitely easier when you actually solve the integrated stuff. So how do we get the coefficient of 1 for y prime? Alright, so divided by x is now y prime plus, and then we have to make sure we divide every single term by x. We have 1 over x plus the cotangent of x times y equals 0, because 0 divided by x is 0. Okay, so now we have something that has y coefficient here, and so that means y prime over y is just negative 1 over x plus cotangent x. You agree? Yeah, agree? Okay, cool. So pretty straightforward so far. So now what we're going to do is we're going to integrate both sides. Now we might want to do a little bit of scratch work. Or, oh wait, I have a quick question. So who all took notes on Wednesday? Ah, that's good, good. All right. So what did we end up concluding about the antiderivative of cotangent x?
Natural log of negative values.
Right, so the antiderivative of cotangent was the natural log of the absolute value of sine.
Not negative.
No, it was a negative cotangent on Wednesday.
Oh, yeah. And then
So
for the sake of being like correct, I'm gonna put the integration constant in. So when we integrate here, we're gonna have natural log of what?
natural.
Well, so for the left side equation.
Oh.
And that after we integrate, we get natural log of
Y.
absolute value I.
Just getting those countries out.
Wait, what section is this from? Like,
It's in the class differential equations. Because
Is this 2.1?
warming up.
so max 211. So raise your hand if you signed up for max 211 differential equations. Okay.
I thought this was English ed.
Okay, what's up, Tommy? Welcome to higher algebra. We're just going to cover isomorphism.
I don't know. I was gonna look.
Yeah, your headphones. So we're going to distribute this negative. So what's the antiderivative of 1 over x log, natural log? Natural log of what?
Absolute
Y.
value of x.
I was actually
Natural log plus the natural log of absolute sine plus that constant. Now we have to be careful though, right? Because this was negative and negative. But the reason why I'm not going to do it like this, I'm going to keep it like this, because there's a really, really cool trick here. So, raise your hand if you took algebra in high school.
No.
I did.
I did not.
No, in high
So,
I did not.
the natural log of x plus the natural log of sine x. Hopefully it's trivial that the natural log of x sine x. Because if you add, so natural log plus natural log, you multiply what's inside. So we get x sine x. So that's why we can really, this is really just one natural log here. So we have the natural log of absolute value y is negative natural log absolute value x sine x and then
Get
plus one.
this natural log
Okay.
1 over
Now,
x.
if you really think about it, who remembers the rule? Basically, if you take the negative natural log of something, it's the same thing as the natural log of its reciprocal. So we all get there. So then the step in which we then argue, so we're gonna go here. We're gonna say that the natural log absolute value y is gonna be equal to the natural log of absolute value y over x sine x. That's it. So does everybody agree?
Yes.
Okay. So what kind of a problem are we solving?
Initial.
All right, the initial value problem. There's a very good reason why we have absolute value bars here. It's because we will be able to plug in our initial condition and they will know precisely how to interpret our absolute value bars. Pi halves is standing in for x basically. Is x positive or negative here? Is y positive or negative? Okay, so all of our y's are going to be positive, and all of our x's are going to be positive on our solution for this d. So the absolute value bars here can go away because we know that when we substitute in natural log 2 is
No, that's a
positive.
1.
And the natural log of, well, we can also take away the bar here. 1 over pi halves sine pi halves constant. So sine pi halves is what?
1.
Yes, and so 1 and this. So this implies that c is equal to the natural log of pi. So that's a very nice clean constant we get out of that. And then all we got to do is plug that back into the last step that we got the constant from. So the natural log of, note that I'm using just y now. Okay, so are we seeing how you're allowed to justify when to remove those absolute value bars? You can remove them after you found your constant and found the rate which so positive. Natural log y is equal to the natural log of 1 over x sine x. Why did I remove the absolute value bars here? I have this positive. And then plus the natural log of pi. And so all we've got to do is exponentiate and we have our solution. So what's the solution? Y, the function of x, is what?
E raised to the power of 1 over x sine x plus pi.
Exactly. So pi divided by x sine x. Alright? Yes, Josiah?
Could you explain how you got the last step how you found C?
Oh, well, subtract and then do algebra.
Okay, I did that, but I got something different.
Okay, let's see. Maybe I just did a stupid mistake. Natural log 2 and the natural log then you have 2 over pi.
Oh, okay, that makes sense. I said pi over 2. You're probably right then. I bet.
Okay. Do you guys want me to clarify the algebra or do you?
Yeah, go ahead.
Yeah, go ahead.
Just clarify the algebra? Oh, because I could have screwed it up in my head too, so let's see. Natural log 2 minus natural log 2 pi, but ooh la la, we gotta take advantage of our rules. Plus natural log pi halves. What's 2 times pi halves?
Pi.
Okay, so I'm not losing my mind yet. And then now when we look at the solution curve yx is pi over x sine x, there are some obvious discontinuities here, right? Or at least it should scream at you, yo, it's broken somewhere. So where is it gonna be broken?
Zero.
Right, you bring up another one. It's going to be all of the multiples of integer multiples of y. So
Yeah.
let me erase the algebra real quick. This is boring.
What if I know about algebra?
If you love algebra, allow me to introduce the map 401. Okay, Christian?
So for the last step, shouldn't it be 1 over x sin x plus pi? Because you have plus natural log of pi.
Oh, I see what you're saying. So basically, if we exponentiated e to the natural log of 1 over x sine x times, so addition of exponents means you're multiplying by the same base. So cancel, cancel. So you have pi times this. So I just stick the pi in the numerator because it's the same difference. So everybody good on the algebra there? Okay. So now to conclude the problem, since we have discontinuity and we were given an initial condition, we can answer this very, very rigorously. So we can say yx equals pi over x sine x. Now, we know that this is going to be discontinuous. So it's only going to be continuous on the intervals r pi is less than x less than r plus 1 pi, and then r is an integer. But we can narrow it down because what's x equal to? Okay, where's pi over 2 fall? It's between 0 pi and what? 1 pi. Exactly. So this is going to be our interval. So we can say this is true. This is the solution on the interval 0 less than x less than pi, and that is the solution to the initial value problem.
Okay, so how did you know that when you plugged the constant back into the original equation, you didn't have to use the absolute value bars anymore?
Okay. That's actually a good question. So in this case, x equals pi x. So is this greater than 0?
Yes.
So what's the whole idea of absolute value bars is that we only want positive output. We only care about taking whatever we put in the absolute value bars and then keep the magnitude of it a positive.
Okay.
So if it would have been x equals negative pi half, well, when you still compute the absolute value, you would still get positive pi half, but then we would keep the negative sign out front when we talk about the y. So when we get to this step, this would have been negative.
Now, I don't know if this situation would always be true, but like if the interval range, like even if you had a positive x and y value, but the interval for x range from negative to positive, would you have to keep the absolute value bars?
So there's a really cool theorem where basically your initial condition curve. So if you were actually, you bring up a good point. As homework for Monday,
Oh, no.
create a direction field for this curve before applying the initial condition, by the way. So just apply the direction. And then, once you see that, anchor it down exactly here. And then you'll see why it's only going to work on this particular interval. And if you did it in a different interval, you would get a completely different looking curve. Okay, so there's been a bunch of hands going up. So let's pause.
Could you explain the intervals again?
Okay, what is sine of 0? Are you allowed to divide by 0?
Not usually.
So it's discontinuous. What about pi? What's sine of pi? 0. Can you divide by 0?
Right.
So pi halves, which is where our initial condition was posted, is in between 0 and pi. Yeah. Okay. Remind me what your name is.
I was just gonna ask you, like, the sign of homework.
That was a joke.
Okay.
He was like, wait.
Sorry, I was sarcastic. That's name.
So you said you can't divide by 0, right? So what about when x is equal to 3 pi halves?
You make up a good
The
point.
next r.
If we said y is 3 pi,
Oh,
halves,
gotcha.
then we would say, well,
Just for any
Chocolate
integer r,
vodka.
right?
3 pi halves is bigger than pi. And then your universe melts down, and then you just realize you gotta just shift it over.
But that's just because that's not the condition that we use.
Yes.
Wait, can you do that again?
It's very specific initial value.
Can you do the pop again?
If you don't grasp, if you get all your numbers back.
I did 2.1.
Okay, as a class,
What
let's
you were
review what we
supposed to
do on Monday. It was through 2.2.
But today we're doing 2.2.
Sure.
Right.
Yes.
You're ready.
So how do we know when we're supposed to apply the initial value?
Right, but-
Where
Oh, I see. So in constant of integration.
Huh?
If you have a constant of integration, this is saying that when you take an antiderivative, you're gonna have a family of solutions
Yes.
that all depend, it could be anything so long as you have this constant. This constant could be anything. And it would still satisfy that if you took this derivative, you'd get back. So this kind of locks down, remember when we were hand drawing out those the direction fields?
Yeah.
And we said there's different possible curves we could have,
Yeah.
depending on where you anchor it in space. This you can think of as like our little anchor. This is going to say, boom, right here in the direction field is where we are starting, and then we drop from there. So we will always substitute the initial condition right after taking the antiderivative. So after you integrate and you get into some form where you have antiderivative, and our integrate, wow, I did that twice and then okay, integration constant. That's when you know, let's plug that in so we can actually figure out what we're talking about here and then go from
To
there.
define C.
Yeah. Perfect. Right.
Can you just ask
Oh, okay, sorry, it's been a lot.
Pluses.
Yes.
Okay. So I was trying to do it, except I did it slightly a different way. So instead of having that negative equal to natural log, 1 over x sin of x inside.
You're talking about this right here?
Yeah.
Yeah.
I ended up just trying to like solve for y. And like putting like e elevated such and such. And then I got a different value for c. I don't understand why.
Okay, so what you actually bring up a really good point, is that it's basically the question of, does it matter when we substitute for when we plug this in to figure out what C is? That's really what the question comes down to. Answer is that, no, it does not matter. So long as after you have integrated, you can technically substitute in for whenever. What you do have to be is very, very increasingly careful. And the reason why I don't really like to substitute it in earlier, especially when we have lots of absolute value bars, is because then it gets very hairy as to watching your signs. And so it gets really, really easily twisted around, in addition to log rules being generally terrible. And so when we wrote it like a fraction, chances are you got a different answer that after enough manipulation and different substitution, you could probably actually algebraically get it back to this, is my guess. But so the constant, yes, if you were to substitute in here, you would get a different constant for C than as if you had substituted in here. But after then you go through the entire thing and be very careful about watching which interval you're substituting stuff back on, you should get back something like this, or at least similar. Because you might have something in terms of secant, which is totally, or cosecant, which is totally fine. But so long as it's mathematically equivalent to this statement, you're all good. Does that answer your question? And I'd also be careful because I remember when I first learned about separable, I made lots of negative sign errors. So it's like exponentiating negative logs, I did wrong so much. So that can produce a lot of algebra errors too as well, and accounting for the multiplication if I'm supposed to. So maybe, yeah, sometimes it gets lost in all the symbols by the time you've gotten to the end of a problem. So you conceptually understand it, and then you just made a mechanical error somewhere. Right?
What's red? R-E-Z.
Wait, I wrote that word down?
It's not what you
R
wrote.
exists in the domain of all integers.
Oh, yeah, so R is an integer.
R is an integer.
Yeah, so R in the set of integers, and Anna here loves algebra.
Yeah.
And well, I guess we have something in common because
I was trying to convert one.
algebra.
That's algebra?
Yeah, so
Okay.
close. It's like, well, discrete is algebra.
If I were to
Maybe
Google,
the first bubble.
if I were to Google algebra, would I find that?
Well, if you were to Google algebra, you would probably get an advertisement with like duplex blocks.
Yeah, I'm trying to
the
figure out how to find out more
Pythagorean
about that.
theorem.
Pythagoras stays.
I'm like,
What kind of toys?
you can find some friends, they have no idea
What kind of childhood did you have?
Played chess before you could read.
Pythagoras.
Just before you.
Algebra.
Wait, no,
We have an A value.
I want my right triangle.
B is
Bro,
probably.
I didn't even do it.
Can we bring purple
Did I
pen?
hear this class? You want to make it 14 hour final? It was on the news.
1 for 0 today, that's pretty good. All right.
Calm down.
Yeah.
Alright,
She was in my class. She said she liked
1
Galen.
plus x squared y prime plus
Mike during
4x
Why was it 14 hours?
Well, it wasn't like that when they were in
2
person, but that's when they switched to
over
online,
1
so I don't know
plus-
why it was. They had 24 hours to do it, but it took a lot of people like. 4
Oh,
days.
yeah. Hey, we're not doing this problem.
Okay.
Wait, what?
We're gonna do the harder problem instead.
Yay.
Plus 2x. Why would I do your homework for you, sir?
I like that.
We love
This
us.
is like 400.
I thought I'd ask about the question.
I'll buy yourself one.
1
One.
plus
I got you a
x squared
cupcake.
y equals x over 1 plus x squared. Squared.
Homogeneous.
And then y 0 equals 1. Did someone just use a vocabulary term?
Oh.
Okay, 1 brownie.
Let's go. I see one.
Let's like you said, this is a non-homogeneous first order linear differential equation. Why?
Because it's not equal to 0.
Well, a better answer for that question is that because it satisfies the definition. Y prime plus a function of x times y is equal to a function with respect to x.
And that's why we can't just divide it all by e to the x over 1 plus x squared, just to make it equal to 0.
Wait, did
What?
you assume that you can divide a number to get to 0?
There it is.
Okay, so.
You're right, my bad.
Once we need a little bit of procedure. So normally we want to get the coefficient to 1. That's already.
We
been
did
done.
it.
Yay. Now what
We solved world hunger.
Calm down.
is, since this is non-homogeneous, we need to first
Make it.
find
Congruent.
y1, which is going to be a solution to
Hot
the
sauce.
complementary
No.
Why are they all
I'm sorry.
negative? Can they not be
equation.
negative?
So who was here on class on Wednesday when we talked about complementary equations?
And that's a y1, not a y comma.
Yes, that's a
Got
y1,
it.
sorry.
No, you're good, thank you.
I'm trying to like work on my handwriting because it's really bad. So we have y1 prime plus 2x over 1 plus x squared times y1 equals 0. This is a complementary equation, okay?
Cool.
Do we follow?
Yeah.
We derive that from the non-homogeneous.
Yeah, basically we just literally copied this side of the equation, drop this off to 0, and then we have now what we define as the complementary equation.
X
You
squared
can
squared.
just get rid of it.
For now.
For now.
This is
You're
the
gonna
homod. We'll go back to it.
Oh, he's just writing the example. Oh, never mind, sorry.
No, that's the
I
concept.
thought you were doing something else.
Okay. So we can actually find the solution y1 now. And so y1 prime over y1, that's pretty easy. We just do negative 2x over 1 plus x squared. Yes, sorry.
Okay, sorry, I'm still kind of catching up here, but the reason we know it's a homogeneous equation is
Which one are you talking about?
the original,
This is not
or
homogeneous.
non-homogeneous. The reason we know it's non-homogeneous is because there's a y prime at the beginning and then a function with only x's next to a
Times
y,
y, yeah.
times y, and then on the right side of the equation, a function with only x's.
Yes, that's not congruent to 0.
Okay, and first order means it's just y prime,
Right,
one
the
one.
highest order derivative is only 1 derivative.
Got it.
Cool, cool. And it's linear because we add stuff. And that's about as straightforward as it is. All right, so raise your hand if you took calculus 1. All hands should go up. So when we anti-differentiate negative 2x dx over 1 plus x squared, it should become increasingly obvious what we need u to be. This. Because now this literally hands us, this is such a gimme. Because it's just 2x dx. Right? So in other words,
Beautiful.
this is u. Well, no, this is du, and this is u. So what's
Wonderful.
the integral, or what's the antiderivative? We have du over u.
Natural log of u.
Absolute value of
Absolute
u.
value.
Whoever said absolute value gets like a brownie point times 3.
So
So
3
three
brownie
brownie
points.
Is it y prime one or y1 prime over y1? Is that what that is?
Yeah, that's a,
Just making sure.
I should go back to grade school. Fix my. So, now what was u defined to be?
1 plus x squared.
1 plus x squared. And for the sake of being correct, okay, now
But we don't care about the c.
I have a question for you. What's the whole point of absolute value do for the sign of a function?
Makes it positive.
Positivity. Now, is 1 greater than 0?
No.
Allegedly.
Maybe.
That is the right answer. And is x squared greater than 0?
Yes.
Allegedly.
Depends on what
Yeah.
x is.
Unless it's
Yeah,
zero.
Okay.
Unless it's
For
zero.
everybody
take
who
the
said
square
yes,
root.
Unless it's
Unless
zero.
imaginary.
Zero.
what, okay, is that a?
Yeah.
So, what can we conclude about 1 plus x
It'll
squared?
always.
It's greater than zero.
Greater than 0. So if the input is already positive, it kind of makes these guys really useless. So it's like the absolute value bars are the third wheel when you make friends with two people who start dating, and then kind of a bummer. So
That's on a personal note.
Do you have something you need to tell us?
okay, so now this negative is ugly. So let's just call this natural log of 1 over 1 plus x squared.
I love
Okay.
that trick.
Now, does it, so this is where in math, you just have to do it. So earlier in the other problem, we weren't able to eliminate the absolute value bars immediately. We actually had to substitute the initial condition in to know that we were allowed to do that. In this case, though, it actually is just more mature to recognize that 1 plus x squared is only positive, so you can just get rid of those.
Hang on, how did you get to is the reciprocal of the inside there related to the negative sign going away also?
Yes.
Yeah,
that is how that works.
It's a little, yeah.
Nate, what's your last name, Nate?
You win.
Nate, yes. The negative natural log of a.
Right.
The natural log of 1 over a.
Let's go.
So maybe they should make this a prerequisite class. Okay. The natural log of the absolute value of y1 equal to the natural log of 1 over 1 plus x squared. Now, you might be like, we need the constant of integration. Fine. We're solving the complementary equation, which means we only need one valid solution y1. So a valid solution y1 would be the constant of integration is just 0. So you do not have to show a constant of integration for the complementary section of things, okay? Please show the constant of integration when you're actually solving for y, but when you're just doing the complementary equation, we can assume the easiest case scenario, because we're just trying to find one possible valid solution for y1.
Right.
So in that case, since we only care about one valid possibility, the absolute value bars, once again, logically are just kind of irrelevant, right? You just choose a y1 to be 1 over 1 plus x squared, and this is a perfectly valid complementary solution, right? Because this satisfies the complementary equation, and we only need one equation that does so. Yes, Alex?
That's because of positive.
Yes, it's because, well, if you exponentiate it, you would get this equals what's inside of that. And
So you can both eliminate the absolute value bars around the y1 and eliminate the constant, or make the constant equal to 0, because you're just trying to find one.
Exactly, we only need one solution that's possible and that follows the rules. And generally the most simple, because you're gonna have to do calculus on whatever curve you just got. Yes, bro?
Where's C right now?
Well,
Do we
so
just start away?
we said let C equal 0. Basically because we just need one possible solution.
Oh.
Yeah, we don't need the whole family of solutions yet. Yeah. Okay, so does this make sense how we get to this? Because this is an important intermediate result.
How do we get to just y1? Wouldn't it be 1 over y1? That's
Not when
the
you-
plug. I mean,
It's what prime over one.
right, right, because we integrate. I know that part. I mean, when you integrate both sides.
Oh, so this part, that's why we did the side work. Because we were
Yeah.
looking at the antiderivative of this.
Yeah, that's the right side. I mean the other side.
He means the left
On the
side,
left side?
the
The
y1.
y1 prime over y1. Because we would integrate that.
And we get the natural log
Yeah.
of the absolute value of y1. Then we exponentiated it.
Oh, that's why that big E is there.
And because it's
So you separate them,
right.
then you're multiplying y.
I'm not sure why it's not.
Oh,
It's in the
why-
reciprocal. I'm not sure why it's not in the reciprocal. It's not.
So if we have 1 over y1 dy.
Right.
The natural log of the absolute value of y1. Then we do this, and then we exponentiate it.
Okay.
Because
And then we just chose an
Yeah.
arbitrary.
he sent the dx
Yeah.
on the bottom to the other side.
Right. Right. Okay. Yeah. I screw up my logos.
Alright. This makes sense, because I'm about to erase this for the room for the rest of the
No.
We're good. Oh,
Wait, was there a question?
No, no question, I'm just saying you're about to raise it. I'm saying.
oh, we're good. Yeah.
Oh, okay.
Yeah, he was trying to write it down. Like, you don't have to erase it.
Wait. So I wasn't supposed to erase?
You're good,
Nothing.
you're good.
Yikes.
Okay, so next up in our procedure, we found y1. Now we need to remember that we are looking for y equals u, a function u times y1. Okay? And then we're going to basically solve for this. So y1. So y is equal to u over 1 plus x squared. This is a perfectly valid definition right now for u for y. Because all we did was we took this guy and multiplied it with u. So do we follow that step?
Yeah.
Okay, cool. So now we want to find the derivative y prime. So how we're gonna do that is we're just gonna make it easier on ourselves. Because which one do you like better, the quotient rule or the product rule?
Product rule.
Yeah, product rule is way cooler and easier. So 1 plus x squared to the negative 1. So then when we solve for y prime, so then here I'll add this to the procedure. And differentiate y. Because you want something for y, you want something for y prime, but ultimately at the end of the day, we're trying to plug stuff back into the original equation. So we have u prime 1 plus x squared to the minus 1, and then plus u times the derivative of this, which is going to be negative 1 plus x squared minus 2 times 2x by the chain rule. So is this step from, make sense?
Where are we getting u over 1 plus x squared?
So in the procedure, what we do so like after we do this,
Yeah.
the next step is we assume that y equals u a function times this. So that's an assumption we're making. That this is how we're defining the solution. And so we're saying, okay, so after we make this assumption, what do we now have when we multiply u with our y1? So that's where we're getting this from. Is that clear? Awesome, great. And then all we gotta do is just simplify some of this because it's ugly right now. We have u prime 1 plus x squared to the minus 1. And then we have 2xu, and that's going to be negative. So minus 2xu 1 plus x squared. There we go. Do we agree on the algebra? Perfect. Now, we get to substitute it back into this equation. Okay? So what's y prime? Well, we just figured out that this guy right here. So let's put it in. So y prime plus 2x over 1 plus x squared y. Now we substitute. So I just wrote down this side of the equation right here. And we're going to substitute y prime into y prime and y into y. So conceptually, do you see what we're about to do?
So step 3, substitute.
If you want another step, yes. 3 sub y prime and y into original equation.
Thank you. Yeah.
Cool. So now let's see. This is basically just now a bunch of alphabet vomit that you scroll through. So we have u prime 1 plus x squared minus 1. And right now I'm literally just copying down, substituting it for y prime. I'm not doing anything different. 2xu 1 plus x squared minus 2. And then now we want to add 2x over 1 plus x squared times y. Well, this is y. So times y. 1 plus x squared minus 1. Now, 1 plus x squared in the denominator is the same thing as 1 plus x squared to negative 1, right? So if we combine these two, we end up getting 1 plus x squared to the negative 2. Do we agree?
Yeah.
And then 2xu, so really this is equal to 2xu times 1 plus x squared to negative 2. You didn't get it, so what can we do now?
Cancel
Cancel what?
with the negative 2xu.
Oh, clever.
That is what I got stuck on the homework.
Isn't that beautiful? Doesn't this make you want to do
No,
math?
but homework.
That's
Is that just a coincidence or is it all like?
in this case, kind of a coincidence. Now, that's why differential equations are so hard in the real world, is because there's an infinite number of combinations of these functions. And so finding these really nice exact solutions does not come around all that often. So these are very special. These are very special exercises in the text. So right now we have this. Now this right here, identify that was really just this. Right? So it equals what?
The real function, or we're done with the complement, right? We're done with using the complement.
Right. We're now using the actual original equation. So this right here you need to see is this. So if this is equal to this, then this must be equal to this, which also must be equal to this. So now we get a new equation. We have u prime 1 plus x squared negative 1 is equal to e to the x 1 plus x squared to the negative 2.
Alright. So that when you just change the order of how they're written, right?
For which set?
This last one, you just changed the order of how it's written, just instead of EX.
Oh, yeah. And I also am realizing that I miswrote this in my notes, so apologies. This was always supposed to be 1 plus.
It's from the, okay.
Oh, that changes.
Okay.
Yeah.
That changes.
I have 2 exercises that have 1 plus x squared in the denominator, and they have different.
That changes a lot.
Yeah, well, because now look at this. We can
I was like,
just-
oh my gosh.
No, the function over there, u prime, 1 plus x squared.
This,
Yeah, is that also negative?
I got that. Okay.
this is equal to y prime.
No, at the end, where you put a -2, 2x, -2xu.
Oh, this was because we were simplifying the chain rule.
Okay, okay.
Yeah, so this right here is part of y prime. We were computing y prime.
Is this basically like a giant U set, like what we're doing, like this whole problem?
No,
Okay.
we're doing variation of parameters, if you remember that term from last.
Yeah, okay, because the U and the Y1, and I was just thinking,
Oh, well, I mean, this could have been an omega or a zeta. Or
Yeah.
a what? Yes, I should do that one of these times. Yes.
So is our end goal solving for you now?
Yes, because note that if we solve u, I can add this to the procedure now. So once we solve for u, all we gotta do is substitute it in again, right? So solve for u and sub into y equals u y1. And then that's the solution. Caleb,
We didn't find you either. We have you prime.
you didn't find me, but I found you. Okay.
Yeah. Negative, like, how do we -1, -2, like if the u prime.
But that's -2 because it's a chain rule, that's why.
Yeah,
Because
negative
you just cancel like at the bottom of the, like have u prime and just something cut equals the other to x. See that?
Are you asking how we cancel these guys out?
One line.
This one?
Yeah.
Oh, because 1 plus x squared -1 is like, just treat this like it's a certain number, and then we divide both sides by that. and
That's
that-
the second one's supposed to be -2.
The main equation is back to, it was, he just made a
Yeah,
mistake.
Oh, yeah, so I have several exercises written here, and then I screwed it up, so that's my bad, sorry about that. It's supposed to just be 1 plus x squared.
That's what's.
So it's like a -2, then you cancel it.
Oh, no, so in other words, what I'm saying is that I made a boneheaded mistake when I wrote the exercise down. I put this, so I had it like this, but I was mixing it up with a different exercise, yeah, sorry.
But luckily,
But luckily, it didn't matter until.
right, we haven't used it yet.
It doesn't affect the entirety of the rest of the solution is not affected by that. Yeah. Okay, cool, so this is the easiest part of the problem because the antiderivative of e to the x itself. Yes. E x plus c. And so what we would do is we would substitute this back in.
oh, and then we can find C with the first order.
Exactly, so then y, well, since this is these, let's do it right here. Y is equal to e to the x plus c divided by
1 plus x squared.
1 plus x squared. And then do you see how you would just put the y equals 1, and then you put x equals 0 in and solve for c, you're done. But she brings up a really excellent point, because I'm going to use that as to illustrate something really important. Suppose you weren't able to cancel that, okay? So suppose this was the way the exercise was actually written, okay? So if Dr. Lang's like, I'm gonna troll these little children so hard. So suppose you do get stuck with something like this where you can't cancel, okay? There is a way to get around this. So, although we aren't able to cancel it, we can still take advantage of the general concept of calculus. So, if we now transfer, so if we basically cancel this out as much as possible, u prime is going to be equal to what now?
Into
X times 1 plus x squared to the -1.
Yeah.
Let's see, right, wait, 1 minus, so yeah, it would be e to the x over 1 plus x squared.
Let's see. Wait, never mind, just kidding.
We haven't had that differentiated yet.
Just wait.
So, you might be thinking, okay, well, let's see what happens if we try to solve for u. Well, this is not integrable, but this does not mean this is wrong. Hey, mathematically still, the correct answer was constant. Okay, so how do we do with this? We're gonna, let me show you how to do that, because this is actually going to probably be on your first exam, so you're welcome.
Same question.
Well, why would he copy the question from the homework?
He wants to.
Is it okay if I remove this intermediate stuff, like, because I am running out of room?
Yeah.
Okay,
Oh, well.
Everything
It's okay.
above it, the bottom line.
I can picture it.
yeah, I'm just this stuff, because I just need a little bit of space to show the rest of this. It's because now, y is equal to u, okay, so this hasn't changed. So what happens if we substitute u in that, right? We have c plus the antiderivative of e to the x over 1 plus x squared dx times basically 1 plus x squared to the minus 1. So this is currently what
So
our
you still
solution
have
is.
just the C that you're still solving.
Right, we still need to solve for c. And you might be like, well, how the heck are we gonna do that? We're gonna do this with a little bit of fundamental theorem of calculus. So y is equal to 1 when x is equal to 0. We're gonna get a dummy variable involved here. So y is equal to 1. Here's c. Now, this is really what we're really doing here is we have, actually before I can plug in this up, because I'm really doing 2 steps at once and that'll be confusing. So let me bring it down. So we have y equals c plus, it's really an accumulation function. 0, so some constant to x, and then the dummy variable inside telling you what you're accumulating over.
And just be 0 to 0.
1 plus x squared. So do you see how we went from this to this? This is just exploiting fundamental theorem of calculus. There's a very explicit reason why I chose this constant. You can choose any constant for that matter. I chose it because x equals 0. So there's going to be a really nice substitution trick. Is that now let's substitute in our initial condition. What's y equal to? 1. C plus integral 0. What's x equal to?
0.
And so we know that the definite integral from anything to itself is just going to cancel away. So you could have put something different in here, but then you would have done a pointless step because then there's no way you can evaluate that definite integral. This is the only definite integral that we know how to compute over this integral.
It's always integral.
And then let's see, 1 plus 0 is, so we just have 1 times 1. And so what then is c?
C is 1.
C is equal to 1 because this goes away to 0. And then we just have c times 1 equals 1, so c is 1.
And we can only do that funny integral skip because the initial condition is when x equals 0.
Exactly. Now, what if the initial condition would have been instead y of pi equals e? Right. Well, then all you would do is make this constant pi. Because then once you plug in x is pi, pi to pi still goes to 0. You still get the cancel
This
away.
is really powerful.
So here's the trick. Exactly. When you do this, when you take advantage of this integral thing, always choose the bottom constant to be exactly the x you want to be eliminating from the initial condition. Yes.
So why does that c equaling 1 matter? Because we just changed the variable. This is our dummy variable. So how do we go back to our original equation with that specific constant?
Oh, so this c is going to be the c found right here.
How though? Because we have e of t.
Okay, so the explanation is fully written out in Calc 1. So the evaluation form of the fundamental theorem of calculus says that a definite integral that you start at some constant, any constant k, up to a certain variable x. So x is the variable. So it's a notational convention to change the letter we use inside the integrand.
Yeah.
But it's actually still the same exact variable. So mathematically, the t's are x's. It's just that we have to shift now because of the fundamental theorem of calculus, so that this now accumulation function, our representative variable, is now standing up here, because that's what's going to be varying. That's what we're choosing up here for the initial. Yeah, but yeah, we did not change the integrand.
Yeah.
So the t is it's like a placeholder. Like we have to choose some random symbol to go in there. While
I get that part. I was just making sure it's-
yeah, no. So whatever c you get here, doing the dummy variables will not influence what the c is. The c will still be valid, so you can forget it. Let's see, Garrison.
How can you just choose the bottom part of the integral? That's what I don't understand. Like you're just saying like you're just saying like, oh yeah, do like pi versus do pi at the bottom.
Because by the fundamental theorem of calculus, you have an accumulation function a of x. It's a definite integral starting from any constant a. Sum up to whatever x is of your function within this, again, this dummy variable is just steps standing in.
Basically, making it kind of convenient for
So
yourself by
yes,
choosing.
exactly. If you're an engineer, you should know it. We make problems easier for ourselves to solve.
You should have seen statics, bro.
Just wanted to clarify, were you just kind of going down a rabbit hole on if the denominator of e to the x over 1 plus x squared, all of that squared, like if it was squared?
Yeah, so basically, in the event that you weren't able to just cancel away and anti-differentiate, so if you're forced to use the integral form of the solution, which is just as prevalent and common in differential equations as getting nice, well-behaved antiderivatives, know how to do both. So my mistake reminded me that y'all need to know how to do that because it's probably gonna be on the exam. Okay?
So why are we, if we're just gonna cancel out our thing that we can't integrate, why can't we just ignore it? If it just goes to 0, we just use that trick every time it's here. Why can't we just,
So
why the extra step?
that's a really good question. It's because, so remember that normally we would like when it was just u prime equal dx,
Right.
well, we could directly, we had a symbol, we had a function for that antiderivative. In this case, the symbol for the antiderivative is this whole disgusting plus. So this is not an arbitrary step. We do have to say we have an antiderivative. And then it's the same thing. So if
I
we
just
had-
mean when you're solving for C.
Oh, okay. Well, it's very analogous to solving for C if, like, say we had the previous situation. You still have to substitute x in here
Right.
and then solve for C. It's the same exact concept. You just need one more intermediate step because now we're dealing with the fundamental calculus. So it's just like a little bit more mentally involved.
So basically, we're just making sure that when you do substitute x into the antiderivative, it just happens to be 0.
Exactly. It happens to be 0. Yeah.
Okay.
So now we can actually write the solution out. It's going to be, we don't need, well, we do need that. Okay, well. Do you have the procedure stuff written down? Because I can clear some space out for the solution. Now we can say that the solution y equals uy1. So u is going to be, since c is 1, c is 1 plus whatever the antiderivative happens to be of this guy times y1. And do we have to worry about restricting the domain at all? No, because once again, 1 plus x squared is always positive. There's no way you can make that 0 unless we're talking about complex numbers. So that's why, but it's generally implied that we're doing x in reals when we're doing differential equations. We're differential equations one. So,
Nice little
Final answer?
yes.
This is the answer to your flubbed up initial,
Yes.
right? Okay. What was the answer to the actual one? I
Oh,
didn't get that.
Oh,
okay.
the proof is left as an exercise
To the reader.
Come on.
Okay, don't tell me you can't substitute it to
It's just,
Do you really want me to, that's like, okay. I could really.
all we have to do though is solve for C. And
Yeah,
then
you're really just putting that u back into, it's actually much easier than
C is
that.
just 0.
Okay,
So in the harder one, you just have an integral in your answer, I guess.
so yeah, you just follow the same exact procedure, you just substitute it back in, substitute initial condition, get a C.
Question. But don't change the boundary, which that is though, or is that just?
Well, actually, that's a really good question. So is 1 plus x squared ever gonna be 0? So can we ever break this? Oh, alright, so then it's x equals.
Okay, so I think we know.
The question in the back?
Oh, my bad. Did we not put C in our final equation because we already found that C constant?
Right, so we don't need the constant in the final answer if it's an initial value problem. If they didn't give you this piece of information, then we can call it a day sooner because we don't need to do the extra step of actually computing what C is.
So we put in the initial value when solving for y1.
Yes.
Hey, you just like that, they have solid, like that control, I think it's helpful, right?
You're talking about U equals.
Are we doing the one where the antiderivative was nice or the ugly one?
Well, the one that was nice is, I already wrote it, but I mean, even the ugly one, I think it's solvable, right?
The e to the x over 1 plus x squared. Yeah, right there.
The one in the square.
Partial.
Are you wanting to use tabs? Because if you want to tic-tac-toe this bad boy, you got a negative exponent, which means you'll never get to 0. So this is not a polynomial that's well behaved.
I was thinking of having like one thing multiplied by the other, and then you do integration by parts.
Well, yeah, tic-tac-toe is integration by parts. So he brings up an excellent point.
We love tic-tac-toe. Go.
Tic-tac-toe.
Some of you know.
Go.
Okay, so if you have, basically we're looking at e to the x, and you're thinking, why don't we just do this, right? Because then we can do integration by parts with this integrand. The problem is, this is a polynomial. And when you take the derivative of something with a negative exponent, you will never be able to resolve that to 0. So what's the first derivative of just this part?
Negative 1 plus x squared, negative 2 times 2x.
And then, oh no, we made the problem worse. And then if we kept on differentiating this, it keeps getting scarier and scarier and scarier. And then you're never able to actually reduce IDP for this. But if what? Well, would you like to add, well, okay, we could do that. Actually, let's try that idea, right? So if we exponentiate e to the x, well, that's straightforward, right? But then you have to anti-differentiate this guy. So the first antiderivative isn't so bad because it's just arc tan x. And then now that's a pain in the butt.
That's never going away.
Very, very, very sad. So you'll never be able to, yeah, unfortunately, whenever you have something raised to negative exponent, you'll never be able to tic-tac-toe. Okay, well, it is 3:44.
Woo.
So I will let you out at a time, well, that's like it's 3:45, all right.
So we never did 2.4?
No, but I think it was definitely worth going over these exercises. Because
Yes. I didn't say for 2.2.
it's all, I love these things.
Yeah.
Lecture distance.
I do have a.
Yeah, but that's fine.
Yeah.